Thank you very much. So I'm delighted to be here. Everything you are going to say is joined with lecturing to and Yuji Shu. I'm going to speak about prismatic F gauges. So this is a category attached to any formal scheme or CE, satisfying some mild conditions. So this is a symmetric monoidal infinity, stable infinity category. It universal home for cohomology theories for schemes over X. That is, if I have a scheme Y over X, there is an associated F gauge, and you can recover all cohomology theories of this Y, at least all cohomology theories I know about, from this prismatic F gauge associated with that. So because of this, because it's kind of so universal, it remembers a lot of information about your scheme Y over X. So this must be a complicated category. And so the main result I'm going to explain is a description of certain full stable infinity subcategory of this category. In the case when X is a smooth formal scheme over Z. And I will kind of formulate a special case of this theorem, just in the case when X is ZP itself. So I will consider what's called perfect F gauge. I will say a couple of words about this. So this will be over ZP. I will look at the full subcategory here with that consists of objects whose Hodge-Tate weights are from 0 p minus. So I recall what this condition really means. And then the theorem is that this category is equivalent to the bounded derived category of Fontaine-Laffaille over Z. Okay, so that's kind of statement that I want to explain, at least the meaning of this. And I also try to explain its generalization. Say a few words, well, maybe not a few, just will kind of explain what the category of F gauges is comprised of. So I will not give a full definition of this category, which is constructed in the work of Drinfeld, Bhatt-Lurie. So, but at least I will say something. Okay, so the format of this construction of F gauges is very beautiful. So with any scheme X, formal scheme over ZP, one associates a stack, a formal stack over ZP, and the category of F gauges is defined to be the category of quasi-iterations. So so this construction is functorial, and in particular, if I have a map from y to x, that means that if I have a map from y to x, then it gives me a map from the syntemifications from this text, and and the FH associated to y is just the RF closed up sim construction. That's how the construction works. Still, it's not very informative, maybe. So I want to give you some examples. Recall for you some examples. Well, the first example, which is goes back to so my x is a spec of K, where a characteristic of K is P, and K is perfect. So in this case, the theory was discovered by Fontaine and Janssen, I think in 1993. The paper was published some 26 years ago, I think, after Fontaine death. I don't know why. So we decided not to publish it, but there is an archive clipping which is there. So so they by analyzing linear algebra structure on the crystalline cohomology, they invented a new cohomology theory. Well, in the kind of enriched crystalline cohomology theory for schemes over. So how it works? So suppose I have y over k, say smooth for simplicity. Then I can consider R gamma Chris, so the complex that computes crystalline cohomology of y. So this is this leaves over each vectors, and it comes together with a Frobenius section, and it also carries the Nygaard filtration. So Nygaard, and well, by filtration on the complex, I will just mean a collection of complexes numbered by integers and maps like this. So, and well, this decreases the gradient, so I will call it V minus, this maps. And this comes together with a extra structure, namely the Frobenius restricted to the I term of the Nygaard filtration is canonically divisible by p to the r. That means that I have a map phi I from which is Frobenius linear. So everything is over double graph K. There is a Frobenius, and this map is Frobenius linear. R gamma Chris. Effects. And the relation is that if I take V minus to the ith power and compose it with phi, then I get e to the I times phi. So you think of this phi I as the Frobenius divided by p. And so there is another piece of structure which can be expressed by saying that this filtration is a refinement of p-adic filtration. Well, when you work in this kind of complexes in derived category, it's actually it's a well, if it were just a kind of torsion-free ZP modules, I would just W of K modules, I would just say that multiplication by P maps the ice term of the filtration to the smaller. So in derived category, it's a structure, and it can be best expressed as follows. So you have, in addition to this maps, you have also a map in the other direction, which I will call V plus. And the relation is that V minus V plus equal to V plus V minus, and it's okay. And finally, so I have this guy. So I have divided Frobenius, and so if these are structures, and now there is a property which says that if I greater than dimension of X, let's see, greater or equal, then this maps field I to field I plus 1 all isomorphisms and quasi-isomorphisms, and also phi I, which is a map from I and to Prismatic cohomology gamma pris is quasi-isomorphisms. So that means that this sort of filtration stabilizes well in the sense that I explained it, and so right. So for large I, this makes sense. Okay. And are there any questions?
Dimension of y, right?
Say again.
Dimension of y.
Dimension of y. Think of it. Yes, of course.
That map is like the other way, or like the map from fill I plus 1 to fill I, or
this is V plus. Thank you. Okay. Very good. So, and this can be kind of formalized, kind of this linear algebra structure can be described abstractly. So let me do this. So I will define for you the category of F gauges over K. And so again, so this will be the main example. So the definition is the following. I consider so objects of this category. Again, this is a stable infinity category. So this is a graded module. Over the following algebra. So it's W of T adjoint V minus V plus and the relation is that the commutator, the product is P. So, and I want to consider graded modules. And also I want it to be P complete. So it's a graded module over this algebra, and as you see, this is an example of a graded module over this algebra. So this relation tells me that it's indeed a module, and now I want to encode this information. This divided Frobenius. So here is how I want to do this. So this will be phi is going to be just one map. It's going to be an isomorphism. Now W of K linear isomorphism between n infinity and negative, right? So this is my phi. Well, it's not this phi. It encodes all phi I for I is together with all these conditions. So now I have to tell you what n infinity and negative infinity are. So n infinity is defined as colimit with respect to along v plus maps of ni. Sorry, and negative infinity is described as colimit with respect to v minus along n minus maps of ni. Yeah. Maybe I should say minus here. Yeah. Okay. So anyway, so in this example, n negative infinity is this. So I can extend this diagram to the right just by declaring that this is n0 and negative 1 is equal to n0 by v minus. And plus infinity is field n I for any I greater than dimension. Okay, so that's and well, this very simple linear algebra Vadim describes this picture completely. We do not lose any information. So this is F gauges, and I want to reformulate this definition using this stack approach. And how you do this? Well,
What's capital F? F upper.
Capital
F.
F. Capital F. Very good question. So this is a map. Which is a nice
V minus. V minus. It's only on automorphism. Okay.
Okay. Yeah. So this is because case this is nice. So I don't really. It's just tells me that this map is not W-OK linear, but simple. Frobenius. Okay. So here's how I want to now reformulate this geometrically, and to do this, so let's introduce some notation. Let's denote this this algebra that appears here by some C. Well, one way of viewing this algebra C can be also described as follows: you consider W of K, and this is a filtered algebra equipped with p-adic filtration, and you take this algebra. This we covered this. So the geometrization is pretty straightforward. So first I define some auxiliary step, which is called K Nygaard. And this is simply a formal spectrum of C. So C is a graded algebra, so this formal spectrum carries an action of G. And I take the quotient by G. So V minus has degree -1, and V plus always has degree. Okay? So very good. And essentially by definition, DQC of this quasi-coherent shift. So here, just on this form, on this formal step is precisely the category of gauges. I erase F. So that is this category, the category of graded modulus over this one. And now, so there are two maps. So in order to construct F gauges, so I have to do the following. I consider two maps from spot W of K to this. One is called J plus, and the other is called J minus. These are two open points of this stack. So one is so there are two kind of open substacks. One is given by equation that V minus is not equal to 0, and the other is given by equation V plus is not equal to 0. If you invert say V minus, you get just you get a copy of the multiplicative group GM, and when you take the quotient by GM, you get just one point. So this is one open subset. Again, it's given by equation V minus inequality. V minus is not equal to 0. The other ones. Okay. So and now my K syntonic is then defined as follows. I take this stack and I glue together two copies of this disjoint, well, two copies of this formal spectrum of W of K that sit here, but I use the Frobenius to glue, which is nice. So namely, this will be the co-equalizer of the map from W of K to K map. And the map is one map is J plus composed with the Frobenius, and the other map is J minus.
But in C, is this relation V minus V plus is E in both?
Yes. Yeah. Maybe I was not clear. Right. The C refers to this portion, not just to the polynomial.
Can you raise the board?
Yeah, sure.
Could you just raise the middle board? Sorry, you mind the middle? Could you just raise the middle board up?
Okay,
I think so.
Okay, so okay. Now what I want to say, I will want, well, so basically no other examples. Well, not quite true. So there are a few more examples where this category of F gauges needs a very simple description, and I will mention it in a second. But in general, the format of the definition is the following. So it's this X scene is defined from by first defining some auxiliary stack X Nygaard, and then there are two open substacks which are called the prismatization of X or Cartier-Witt stack of X, and you take the coordinates. So in this case, the prismatization is just this. Okay, so this is okay. Very good. So now I won't tell you construction in general, but I will construct some maps to this prismatization. Maps that I'm going to use. So how it works? So suppose I have a prism, namely A delta, and well, for simplicity, I will assume that the ideal defining ideal of the prism is principal. So this is a prism, bounded prism, and assume that I have a map from formal spectrum. So I take A and I mod it out by D. So this is a p-adic ring, and I take its formal spectrum. Then suppose I have a map. I'll give you a map. Suppose I have a map from this formal spectrum to X. Then this gives a functorial way. This gives a map from this algebra of the p-adic filtration on A. So this is familiar thing. This is V minus V plus and the relation is the product V minus V plus equal V. Not D, but D. So it's p-adic filtration. And I take the quotient by GM. It's graded. And then, so there is a canonical map to even to X9. And if you, so again, there are two maps, J plus, defined similarly, and J minus. And I want to compose one of them with Frobenius, and now this is Frobenius on A defined by the delta structure. And so that's a map from Spaffey. So the property is that if I look at the composition, then the ring. So so that's what I'm going to use. For example, so suppose we are interested in F cages over, yeah, maybe I should say that, so by functoriality, this map actually factors through prismatization, through A mod Z, atomic, and in the case, yeah, maybe I should, that's not what I want. So everything factors. So I could apply this construction to the universal case when X is when this is just the identity, right? So, and then I get a map from this guy to the prismatization of this form of scheme. So the claim is that if A is a perfect prism, then this map to Nygaardization, right? So I get a map from this guy to Nygaardization of this one, that this is already a nice surface. And also Nygaardization of symptomification of A mod Z in the case when A is a perfect prism can be defined as a, well, it's co-equalized. Exactly. So this is a special case of this example. Okay.
Can you repeat the last sentence? If this is a perfect prism, what happens?
Then, okay, so there is a map from here to A mod Z and this map is a nice. Usually I do not write when my scheme is a finite surface. So that's kind of so from this point of view, if you have some kind of perfectoid, then there are good chances to define applications explicitly. But if your scheme is something like ZP, for example, then this is a very complicated. So that's probably one reason why integral p-adic Hodge theory in this setting was first developed for when the base is OC and then over ZP. Okay, so very good. So in particular, so I'm interested in So let's take, let's consider an example. So let's take for x just stuff w of k. So let's look at that gauges here. And well, I can some kind of get some information about this, well, some kind of geometric structure on the simplification by applying this construction. So for example, I can take for A the Bhatt-Scholze prism. And so the delta structure, well, we will describe Frobenius. Frobenius is x to the fifth power, and d, well, it will be convenient. So it's d minus 3. So this is a prism, and so what we get from this is a so map from the formal spectrum of the Cis algebra again. So in the case when x is w of k, so this construction produces me a map from the Cis algebra for any prism that lives over w of k, in particular this one, and I get a map from the Cis algebra v minus v plus d G to the Nygaardization of w of k. And well, in particular, so there are two important substacks here that I want to consider. So, well, so one substack is stuff of w of k v minus mod g. Well, so this map, I think it's clear what it does. So it takes d to 0 and v plus to 0 and v minus to v max. So this is one map. So this is just, I will call it A1 over GM, affine map. And there is another map that I want to consider. So that's let's map this prism A to w of k by sending u to 0. So then they will be mapped from stuff w of k to well, modular v minus v plus, and the relation is that v minus v plus is equal to v. Okay. Okay. So and this is, we already seen this. This is K9. So another way of constructing this would be to use functoriality. So okay, so I'll summarize what happens. So this construction geometrizes the relation between cohomology theory with various enough gauges and the relative prismatic cohomology, right? So if I give you a prism and a map to X and any scheme Y over X, I can pull it back to this spectrum and consider the relative prismatic cohomology, well, relative to this prism. This will be an A module with Nygaard filtration and with a Nygaard refined Frobenius. And this is exactly described by this, as it can be described as a sheaf here. Right? So that's how starting with an F gauge, you can recover all prismatic cohomology for all pieces. Very good. So, so in particular, so I can recover cohomology theory with prismatic cohomology theory corresponding to Bhatt-Scholze prism. And by specializing it further, I can construct a sheaf on A1 homogeneous, which is in geometric context, is nothing else but the Rham cohomology of Y, equipped with the Hodge filtration. So it's Hodge filtered Rham cohomology. And if I specialize it, if I take the pullback along this map, I recover the crystalline cohomology with the Nygaard filtration. Okay, so these are the two important maps that will play a role. And here is a first kind of so this is well, a key result for what's going on, what will happen. Next. So this result is well, I learned it from Drinfeld. Well, if there is any mistake, then this is entirely my fault because it means that I didn't understand what Drinfeld explained to me. So so this is first I will formulate the problem and then I'll tell you that. So suppose. So we have this mysterious stack W of K, Nygaard. And we have two maps. So one map is from something very understandable, right? This is just yeah, I forgot to say that I take the quotient by GX. So this is one thing, and another thing is there is a map from A1 which. Okay. So in the geometric context, so if I give you a scheme over W of K, so there is an associated F gauge corresponding to the scheme. I can pull it back along this map, and I get the crystalline cohomology of the special fiber of this scheme endowed with the Nygaard filtration. And here I take the crystalline cohomology, oh sorry, the Rham cohomology of my scheme over W of K, endowed with the Hodge filtration. Now there is another arrow in this picture, namely there is a Rham map. I will call it T. And it should be clear, this definition of this map should be clearer from my notation, right? There is a map from this algebra here to this algebra, which just takes V minus to V minus, right? The most obvious map. So this is this. So it's this is. So now I have a question for you. Is this diagram commutative? It cannot be commutative because, so what would it say that it's commutative? So what does it do geometrically, this map? So, so the category of quasi-coherent shifts here is a category of filtered complexes. The category of quasi-coherent shifts here is also a category of filtered complexes, but the filtration is a refinement of the p-adic filtration, right? So if I give you any filtered complex, there is a universal way of making it a refinement into a refinement of p-adic filtration, right? So if I give you like F0, F1, F2, you just take new filtration. Well, for the first term, you take F1 plus P times F0. If it's everything, it's not. Well, but geometrically, it's described as a pullback, right? So if this diagram were commutative, it would mean that the Nygaard filtration on the crystalline cohomology is obtained from the Hodge filtration on the Rham cohomology by downgrade, right? By this procedure, by making a filtration forcing it to be a finite of p-adic. And it's known that it's not the case. However, there is something, well, it's also known that in small degrees, it is the case. So, and here is a precise assertion. So I will introduce in algebra. Okay, so I will introduce algebra B, which is which is going to be a subalgebra of C tensor, and I recall that C is this algebra. This is right. This is my C, and so this is a W of K subalgebra. Generated by V minus, V plus, and V plus to the n over n factorial. N goes over all integers, right? I get some divided powers. So this is a graded algebra, and so you can compute its well, one way of describing this graded algebra is the following: take Z W of K. It has a p-adic filtration, right? So, I can consider the ideal generated by P inside W of K, and I can take its divided powers. Maybe I'll put dot. Right? Divided powers of this ideal. That's not the divided power of P, right? This is the divided power of the ideal, but it's different. So this gives me a filtration of this algebra, and I can take its least constant. This is mine. Okay. So you can describe this in each degree. B is free W of K module of rank 1. You can describe explicitly the gene. Okay. So and now, though this diagram is not commutative, yeah, so let's take. So remember that, well, so of course B contains C, right? By definition. I added some divided powers. So in particular, I have this map. And I also have this map. Yeah, because if I, yeah, I think it's clear. So I had some divided powers. Of course, I do have. So, and the claim is that so lemma, which is gain I. So I learned it from Drinfeld, but well, formulated it slightly differently. So it's. I hope it's correct. That this diagram is correct. Well, strictly speaking, we are working with stacks, so commutativity is a structure rather than.
Just to be clear, the dashed arrow is not in the picture.
Yeah, maybe. Okay. Yeah,
it's not.
It's not. Yeah. Yeah. However, it's sort of it helps to explain. So this is an approximation to the commutativity of the original. So okay. So now, proof is not hard. I mean, although this study is complicated, at the end it's given by an explicit equation. Well, the equations are as complicated as the ring structure on the Vit vector sets, right? So it's not well. So at the end, it amounts to proving something about read vectors. And so what you have to prove is the following, that if you take the read vectors of V, then the tabular representative of V plus to the p power is divisible by p. That's how B is. And you do this using some calculus, namely the Taylor expansion for exponential and logarithm. Very good. So now, what does it have to do with my original, with this theorem? Okay, so I need to tell you, I told you something about the left-hand side, but now I want to recall for you this category. And so
did you say a few words about this 0p-2 for you in the left-hand side?
Yeah, very good question. So maybe right. So Hodge-Tate, thank you for Tate weights. So this is so suppose I have a sheet on K9. All right. So this is something that's just a graded module, right? That's graded module over this quotient of the polynomial algebra. This is V minus, this is V plus. So I have Vi and I have Mi minus 1, and here I have and here I have I minus 1. Sorry, plus 1, right? So now I'll say that F has weights greater or equal than N if one of the maps, namely V minus, is an isomorphism starting with degree like all these maps are isomorphisms. And similarly, it has weights less than M if the same is true for V plus maps. So I have N M, and here I have V plus. This is N plus 1, and all these maps are isomorphisms. Okay. So kind of the main idea is that if your F comes from a smooth scheme over W over K of dimension, say M, then the Hodge-Tate weights, well, the Hodge-Tate weights in geometric context are always greater or equal than 0. And they are less than the dimension, less or equal, right? So that's how you define weights here. And weights here on W, so you have a map from, so I will get some names. So this is Roger on plus, and this will be Rockets. So, and I have a functor from gauges on K to gauges on W of K, which is, sorry, which is which is just the pullback with respect to this crystal. And I say that weights are from end to end here, if the same is true for the code. Okay, so that's the definition of this. So weights here are greater or equal than 0 and less or equal than p minus 2. So if I have any scheme over ZP, smooth scheme over ZP, then it's corresponding of dimension less or equal than p minus 2, then it's corresponding to gain leaves.
Sorry, so just to be clear, are you saying so you take a quasi-coherent sheaf on the simplification?
On the prismatization, yeah, on simplification. I pull it back to Nygaardization, and then I pull it back. This, yeah.
So remind me what does these 3 dots mean? Which divides which?
P dots. So this number, this element of the ring of Witt vectors is divisible by P.
Okay, so P divides the.
Okay. Yeah.
The diagram you have like mi plus 1 and then mi minus, and then the arrows kind of start switching orders.
Yeah,
Yes, we got it.
It's supposed to be consistent.
Okay, so
Just want to keep the pattern.
yeah, keep the pattern. Good idea.
You have n rather than m, so that's Nygaard.
I think the N should be capital N should be capital N in the bottom 2 lines. The module is the greater module is M and not N.
Oh, yeah.
Is that right?
Yeah, really. Yeah, thank you.
Big letters should be.
Yeah, thank you. Okay, so now I will tell you what this category is. This category. So this is the subjects are the following. These are coherent sheets, and A1 more GM. Yeah.
So did you say that you define the weights
Yes.
for W of K as the pullback?
Yes. So I define weights here as follows. I take an object here, I pull it back, and then I pull it. So I take quasi-coherent sheets on A1 more GM together with a additional piece of structure, namely, I can take the fiber of this at point V minus, so the coordinate here is V minus. I take the fiber at point V minus equal P. And coordinate here, and then I take the fiber at V minus equal 1. And my extra piece of structure is an isomorphism. So this is a W of K module, and they can raise a perfect field. So I require, so the extra piece of structure is an isomorphism, Frobenius linear isomorphism between the 2 fibers, the fiber over point V minus equal P and the fiber over point P minus equal.
You want to put W of K there or VP?
Oh yeah, thank you. Yeah, that's okay. Yeah. Thank you. Very good. So this is equivalent, though not exactly. It's not how Fontaine-Laffaille formulated this. They didn't use the same language, but it's equivalent. So a nice exercise that was the lemma in Fontaine-Laffaille paper is that, so first say you start with you have a Fontaine-Laffaille module, which is a p-pair. Then select. That is because if you have a coherent sheaf, then saying that it's a vector bundle, it's equivalent to saying that its dimension of its fibers at every point, the same. it's Gm equivariant, so you just have to compare the dimension at point v minus equals 0 and v minus equal 1. But you know that there is isomorphic, so they have the same. Does it make sense? Okay, so now I have 2 minutes and I have to explain for you how you construct a factor. So functor. That will be a functor. Actually, it will be a functor. Yeah, maybe it's even slightly more interesting if I consider B category. So that will be a stable infinity category, and it's defined exactly like this, except that F is now in DQC of A1 much. And then I have, well, phi is the same. But now I take the derived fiber from this Fontaine-Laffaille lemma that I explained to you, I mentioned. So in this setting, in the coherent setting, this kind of abelian fiber coincides with the derived fiber. So the two definitions. But if you really want kind of big category, it's not a derived category of some abelian. And so I will construct for you a functor from DQC 0 p minus 1 of W of k to the category, to this big category of Fontaine-Laffaille. Yes, it's p minus 1. The functor is defined on a larger category, but it's in equivalence only if you restrict this. And how
I
it's
mean like the Nygaard filtered prismatization of WK here, or you really mean
oh yeah, I meant simplification.
Wait, sorry, is this supposed to be obvious? Is MF WK supposed to be the Dewey category?
So this category is abelian. That's a lemma of that's basically, well, kind of the key is to see that the category of p-torsion objects is abelian. I think I more or less explained it. So the key point is V minus is not only abelian, the pullback functor to quasi-coherent shifts on any one more GM is exact. Yeah, but this big category again, it's not a derived category of some abelian category. If you replace coherent shift by quasi-coherent, it's all. Okay, so I will finish by explaining the construction of this functor. So I have the following diagram. I have W of k, symptomic. I have W of k Nygaard. And this is some JM map. That's notation. I have k symptomic. This is, and I have k Nygaard. That's map that we already had. This is p-crease. And then I have A1 more GM. Then we had this map, T. And then we had this map, which is Rham. And then we had 2 points, of W of k. And there are 2 maps that we glue together. So I start with an object here, and what can I do? So suppose I have F, here. I want to produce for you an object of this category. Well, first of all, I need to produce for you this another. So I take, I assign to it rho. Well, I take J up star n, and then I take rho Rham plus of F. Right? And now I need to produce for you an identification between the 2 fibers. Okay, so what you do is the following. So how you define phi? You take f upper star of so maybe let me call this m. So I take m b minus equal to. And first I observe that this is equal to f upper star g plus t star. Then, and this is really the key, I'm going to use Drinfeld's lemma together with this assumption that the Hodge-Tate weights are from 0 to p minus 1, and the fact that the map from C to D is an isomorphism in degrees less than p. So this can be this. Then from Drinfeld's lemma, I conclude that this is Rockley's star J star and F. And then because it comes from syntamification, that's the same as J upper star minus Rockley's upper star J upper star N. Yeah. And using Drinfeld's lemma again, I get that this is the fiber of M B minus. Okay, so what I did for you, so I reduced the map from here to here, and this is my phi. And this gives me a functor. And the claim is that this functor is
If you replace p minus 1.
yeah, by if I restrict it to smaller category, it's going to be. The proof was essentially explained. Well, there are two ingredients. One is a ingredient is this official paper by Drinfeld. This is the description of the reduced locus of ZP W of K Nygaard. And the other ingredient, well, was explained to me by to us by Bargov. It's a deformation theory argument, which says that in small Hodge-Tate weights, the category of quasi-coherent sheaves on W of K symptomic tensor of P is equivalent to the category of quasi-coherent sheaves on the reduced locus.
On what?
On the reduced locus.
Okay.
That's all. Thank you very much.
Other questions? More questions? There are plenty of questions already. Great.
The inverse equivalence.
Yeah,
That's something that has a hope of extending to something that's defined when you don't have this condition on the weights.
the inverse. Let's see. So you're asking whether there exists a functor from the category of Fontaine-Laffaille modules to F gauges. Well, at least I do not have a hope. So there is a paper by Bright and Kess and by Liu, which is called Vertices modules via crystalline cohomology, where it's maybe 2030. So they explain how in the case when if you have a smooth projective variety of dimension less than p-1 over W of K, how using the crystalline homology with some natural structure, Frobenius, Hodge filtration, how you can recover the Vertices module. Well, they assumed actually that the homology is p-torsion. And so it's an ingenious construction using some kind of vector bundle modification on spectrum of the derivatives in prism. But it works only if, I mean, even the construction, well, there is a comparison. There is something then you want to prove afterwards, but even the construction works only if the Hodge-Tate is small. But maybe you can actually comment on this. This construction is due to, well, it's related to.
Not off the top of my head.
So I don't know, but also I should say that for general X, the category of Fontaine-Laffaille modules only defined, well, only this part when the Hodge-Tate weights are from 0 to p-1, and the range is less or equal than p-1 is defined. You can define kind of there is this category is defined. Well, originally it was defined by Fontaine using kind of glue, and his definition works only in small range.
Is it possible to try to do something like the following? So on the left-hand side, replace by quasi-coherent sheaves on WKN, where you look at all quasi-coherent sheaves, not just ones coming from pullback from the symptomification.
Yeah.
And then maybe, I think you can still define Hodge-Tate weights, so the same condition. And then on the right-hand side, it's something like Fontaine-Laffaille modules, but you forget some sort of information about the Frobenius.
Well, but the kind of Fontaine-Laffaille module consists of, well, there are two pieces of structure. You have a quasi-coherent sheaf, and you have this phi. Phi comes from this from the fact that you leave from F gauge piece of structure, right? From F, from the Frobenius. So what I mean, if you forget this, then the sort of the category is not going to be probably particularly interesting. It's just a category of input models.
So you have this Functor for weight 0 to p-1, and what happens to the weight p-1?
Well, imagine that you say you look at p-torsion objects. Look at p-torsion objects. Then and let's say p equal 2. The category of Fontaine-Laffaille modules with Hodge-Tate weights 0 and 1, say p-torsion Fontaine-Laffaille modules, is equivalent to the category of finite flat group schemes over W of k cubed by p. It's true if p is greater than 2. The corresponding category of F gauges is always equivalent to the category of finite flat group schemes filled by Bhatt-Scholze groups. So there is a functor from finite flat group schemes to Fontaine-Laffaille modules. It's constructed in this original paper by Fontaine and Laffaille, which is not an equivalence. If p is 2, it's not an equivalence because the source category is not abelian, whereas the target is abelian. But nevertheless, Fontaine and Laffaille proved that if you restrict yourself to connected groups, then it's an equivalence. So, and of course, any group is an extension of a connected group by some, of discrete group by a connected group. So there is a hope that when the Hodge-Tate weights are from 0 to p-1, the category can be still described in the hierarchical terms. But first one has to understand Bhatt-Scholze groups over Z2.
Any further questions?
You just say a few more words, like how to think about this Fontaine-Laffaille modules, like.
Say again?
Could you say a few words on like the intuition of how to think about this?
It's very simple. So what does this definition? I mean, first you have a filter, you have M, and you have some filtration. This is F0, F1, F2. So you have filtration. In fact, so a lemma a priori, these are just maps. But so one can show is that if F comes together with this phi, then it forces all these maps to be injections. So you have a filtered ZP model, or W of K model. And so what is this phi? This phi can be thought as a collection of maps. So you have this, you have this, so this is phi, this is phi 1, this is phi 2, and so on. The relation is that if you take phi I and multiply by p, then you get v minus composed with phi I minus 1. And so this species of structure is equivalent to given a map from here to here. And saying that it is an isomorphism, well, under the assumption that these are injections, is equivalent to saying that the sum of the images is the whole. That's the original definition of Fontaine-Laffaille. So in geometric context, M is just the Rham cohomology. F is the Hodge filtration. And this divided Frobenius come from Mazur. So Mazur proved that on the ith term of the Hodge filtration, the Frobenius is canonically divisible by p to the I, provided that I is less. That's the intuition.
I propose if we have further questions, maybe we take them to tea. So let's, anybody wants more?